In the last section, we talked about this problem, and it was the last problem in the section. It was a situation where we were discussing the volume of a box, and it was situated so that the far corner was at the origin of our three-dimensional coordinate system. And we had a constraint on the size of the box, and that constraint was in the form of a plane. Now, the plane intersects the various axes at these given points, and the equation of the plane was given in the problem. Now, the constraint was such that the top corner of the box, the corner that is kind of closest to us, the top vertex, is this one right here, and it's right on that plane. And we would like, out of the family of all boxes that can fit into this category, under these constraints you see, we want the one with the biggest volume. Now, the way we approach the problem is this. We said, okay, we have an equation for a plane. We took that equation, we solved for z. Then we put that information into the formula for volume. Volume is x, y, z. We replace z with that expression, and away we go. We bumped into a problem, though, when we took our two partial derivatives. And we want the critical values associated with this, so we need to solve these two equations simultaneously. We have two equations and two unknowns, so we should be able to do that, but it's a tough problem. Now, there's another strategy for dealing with this. If we put this problem into a particular category, into the category of a family of problems, that family called constrained optimization problems. The optimization idea means that we are going to either maximize or minimize some function, and here we're trying to maximize a volume. And the constraint involved here is our equation or our function having to do with the plane. Now, the method, the technique we're going to use here is Lagrange multipliers, and the technique is named after a great French mathematician whose last name is, not surprisingly, Lagrange. But here's what we do. We take our first function and call it f of x, y, z. F in terms of x, y, z is this x, y, z. This is our volume function. And our constraint function is a g function in terms of x, y, z, and here it is. Okay, now we define a new function. Here's where this Lagrange multiplier comes in. We define a new function, and the notation for it is uppercase F, and it's F in terms of x, y, z, and the multiplier lambda. All right, and it is the f function minus lambda times the g function, and that's all there is to it. And now we can simplify things a little bit, replace this with the expression x, y, z, replace this with the expression for the g function. Now we are going to go through the process of taking our little derivatives. You see the derivative of f in terms of x, in terms of y, in terms of z, in terms of lambda. Let's do that over here. We have the partial derivative in terms of x, the derivative of f in terms of x, turns out to be this little expression. And each of the partial derivatives, notice, is a relatively simple little expression. Now, we have no letters that are squared here or anything. It simplifies and streamlines things to a degree. But we still have some challenges here because we are trying to solve this system of four equations in four unknowns. And so we have to figure out a strategy for that. Now, a way of doing it is to notice here that we have an expression that doesn't involve lambda. And we may be able to take our other expressions and solve them and do some replacement and so forth. Here's what I did. I took the equation 1 and I solved it for lambda. Lambda is yz over 6. And that's just from that top one. And then in equation 2, I replaced lambda with this expression, and then I simplified it a bit, and I found y to be equal to 3x over 2. And then I took this information about lambda from equation 1, and I put it also into equation 3, and I solved it for z. Z is equal to 2x. And now I have a replacement in this expression for y and z, you see. And so I use those, and here's that fourth equation. And I bring down the minus 6x. I replace y with an expression for it from down there, replace z with the expression for it from down there. I have this. I find x to be 4/3. Well, if x is 4/3, I can find y and z by popping them back into the forms of the equations over there. Y is equal to 3x over 2 from one of those forms. X is 4/3. So I find that y is 2. And then for z, I just replace x with the 4/3, and I find z to be 8/3. Well, gee, with this value of x, y, and z, I have the volume then is x times y times z, so the volume is 7 1/9 cubic units, as we suspected from the previous time that we worked the problem. All right, the important thing is the application of the Lagrange multiplier. And let me point it out. Let's look at where it turns out. We have this f function that we're trying to maximize, and in some other problems that involve optimization, it might be minimized. And then we have a g function for the constraint. And then we make this, this new function that has to do with this Lagrange multiplier. So it's the function we're trying to maximize or minimize minus lambda times the constraint function. And that's the important part of applying this method. Here's an objective function containing 4 variables. And we'd like to minimize this function if we can. So the objective function is here, and our constraint is this equation. And we go through the process as we have talked about before. That is, we define this uppercase f function as the f of all of this x, y, z, w function, then minus the lambda times the constraint function. And away we go with the process. Now, by the way, I said that we're going to minimize this function. You know, we don't have a way to tell whether or not we have a maximum or a minimum, even after we go through this process. The maximization or minimization of the idea comes from the context of the problem. Generally, we're told, like in one of the problems before, we were maximizing volume. Well, we know that we have a maximum because that's what we were looking for. It doesn't make sense in that problem to have a minimum volume, you see, because we could have another kind of rectangle or solid, rectangular solid, that would give us a very, very tiny volume. But at any rate, it's the context of the problem that tells us whether it's a max or a min. Here we're looking for a minimum. At any rate, all right, we go through this the structure of this function, and then we find our derivatives, our partial derivatives. F in terms of x turns out to be this. And then each one of them has a little simple expression associated with them. Now, there are 5 of them in this case, and we take each of these, and I've numbered them here for convenience, and you set them equal to 0. You say this is equal to 0, and this one is equal to 0, and so on. And then you solve this system of equations. Now, I've used a particular strategy that I can show you here. In equation 1, I've solved for x in terms of lambda. In equation 2, I solved for y in terms of lambda. In equation 3, z in terms of lambda. Equation 4, w in terms of lambda. Now I can take my, my overall function, my function 5, the function that, I shouldn't call it a function as such. It's an equation. It's one of those degenerate equations that involves x, y, z, and w. And I've solved for these variables in terms of lambda over here, and so I just plug in. And now I have a single equation involving one single variable, easy to solve for. I find lambda to be 1/5. And then I do some back substitution. So I substitute this value of lambda back into those simple little equations, and this is what I find for critical numbers. In equation 1, it was x equals 3 over 2 times lambda. We find lambda to be 1/5, plug it in. We find x to be 3/10. And then y is equal to lambda, or 1/5. Z is equal to negative 2 lambda. Replace lambda with 1/5. We find z to be negative 2/5. And so on for w. Replace lambda with 1/5. We find w to be 1/10. And now these are our critical numbers, so we write the function in terms of the x, y, z, and w that we found right here. And that function in terms of those variables is this. The value is 3/10, and 3/10 then is the minimum value of the function. Now it turns out that we can use Lagrange multipliers to solve situations in optimization problems involving 2 constraints. Here's an example of that situation. Suppose we want to minimize this function involving 3 variables, and we have 2 constraints. Well, here's the structure of the equation that we use for that purpose. It is uppercase f of x, y, z, lambda. and it is the given function, the objective function, minus lambda times the first constraint function minus another variable, mu, times the other constraint function. And that's all there is to it. And then we go through those partial derivatives, derivative with respect to x and y and z and lambda and mu. You see, and now we have 5 equations involving the 5 unknowns. We solve the system of equations and go about the business of minimizing or finding the minimum value for the function.